Hey, welcome to the GSU Perimeter College online tutoring review session for Professor Keisha Brown's Math 1111 course. Today we'll be going over the Test 3 review, and we'll be covering sections 3.1 through 3.2, 3.5 and 3.6, and 4.1. And the concepts specifically that we'll be covering are all related to functions, and they'll be the different types of functions, the quadratic, rational, inverse, and exponential, those specific ones, and some of the interesting operations that you can do on them and the way you can analyze them, that sort of thing. And as usual, I will be working from the previous test that she uploaded to iCollege. This one specifically is the test from fall 2015. So let's go ahead and get started. So for this first problem, it says use f of x is equal to 2x squared minus x minus 3 to solve the following. What are the x-intercepts? Well, in order to determine the intercepts of some function, what you do is you set the opposite variable from the one that you're trying to find equal to 0. So in this case, you'd set y equal to 0, and since f of x is equal to y, you'd set that to 0, meaning that you'd set the whole function to 0. And so in order to solve this equation, what you want to do is factor it into, as you have seen before when working with like quadratic functions or polynomial functions, when you factor it, or for like quadratic equations, use the quadratic equation, quadratic function, sorry, you can get the zeros easily that way. So since this is a quadratic function, what I'm going to go ahead and do is go ahead and use the quadratic function. Quadratic equation, sorry. Okay, so the way that's set up is you have negative b plus or minus the square root of b squared minus 4ac all over 2a. And so you plug in your a, b, and c values. B in this case, all of these letters are the coefficients of the x variables here. And just as a little bit of reminder, this is x to the 0, which is just 1, so that's why it shows up as just 3. And this is negative 1 times x to the 1. So a would be 2, b would be negative 1, c is negative 3. And so if we go ahead and plug that into our quadratic equation here, we get negative 1 plus or minus the square root of b squared, so negative 1 squared minus 4 times 2 times negative 3. And all of that is divided by 2 times 2. And so what this ends up equaling when you simplify it, well, the negatives cancel, so that's a 1 here for that term. And then plus or minus all of this stuff, the discriminant here, which would be, I'll go ahead and write it out. So that's 1 plus, because the negatives cancel, 4 times 2 is 8, times 3 is 24, all over 4. And so what we end up with is 1 plus or minus, well, this is the square root of 25. And so I just kind of jumped a step a little bit and went ahead and solved that part. And so that is equal to either 6 over 4 if you add the 1 and 5, or 4 over 4. And that can be further reduced to 3 over 2 and 1. Now, the x-intercepts, you get into the ordered pair form. So your x values are these guys that you found, or that we found here. So 3 over 2. And your y values, as explained at the start of solving this, are equal to 0. Right? So you have that guy, and you have that guy. So 3 over 2 and 0. Excuse me. 3 over 2, 0, and 1, 0. The next question is, what are the vertex coordinates? And there's a later question that's asked in conjunction with this problem that asks you to complete the square to change the function into its vertex form. So I kind of combined these into one problem, because if you're going to find the vertex coordinates, you're going to basically have it in vertex form. So might as well do both at the same time. So what you do is you take the function here, 2x squared minus x minus 3. And remember that, oh, let me not scroll too far. Remember that these are a, b, and c respectively, the coefficients of the variables here, not the x terms themselves. And what you want to do is take this b term, and divide it by 2. Right? And so what that, one other thing. Before you can even do that, you also have to factor out the 2 here. So before you're able to actually do the later operations of getting this into the completed square form, or converting it to the vertex form using completing the square, you have to factor out this 2 from each of these guys. So I'm going to go ahead and erase this here to kind of make my work more explicit. Go ahead and add that b back in there. So if we factor out the 2, we have 2 times, that's not right. Okay, so for the next problem, it asks what are the vertex coordinates? And it also asks later on to use completing the square to change the original function to vertex form. And since it's asking for the vertex coordinates here, I figure it would be a good idea to also combine that with the converting it to vertex form. So in order to get the vertex of the function, what you can do is, you know that x is equal to negative b over 2a, right? And so what you do is you plug in the coefficients corresponding to a and b over here into that. And so that would be 2 and negative 1 respectively. Go ahead and plug those into this guy down here, and you get negative 1 over 2 times 2, which is just 1 over 4. And so the next thing that you have to do to find y, you plug that value into the original function, so f at 1/4, right? Because remember that the vertex is an ordered pair. So you're going to look for the opposing variable's value at a given value for the variable that you know. And since we just found x, we're just going to plug that into the function to find y. So go ahead and do that. Let's see, that's 2 times 1/4 squared minus 1/4. minus 3. And so if we go ahead and simplify that, the 1/4 squared, this guy, is equal to 1/8. Sorry, whoa, not 1/8, 1/16. Because you multiply the top number by itself, and then you multiply the bottom number by itself. And then you multiply that by 2, and minus 1/4, and finally minus 1/3. So the answer to that, excuse me, just had to yawn really quickly, is 1/8 minus 1/4. So it's not quite the answer yet. Still have to simplify it a little bit. And I'm trying not to skip too many steps in order to show my work explicitly here. So go ahead and find a common denominator for all of these, which would be 8. And so to convert 1/4 into something with an 8 on the bottom, you just multiply the bottom by 2. And whenever you multiply a fraction by something to convert it into, or to get a higher denominator or change its form or what have you, you have to multiply by 1. So it stays the same. So if you multiply the bottom number by 2, you have to multiply the top number. So that would be 2 on top, 8 on the bottom, and then 3, converting negative 3 into a fraction that contains that the denominator is 8, well, we can just put 8 on the bottom, because 3 is really 3/1, so it's already a fraction. So you multiply the bottom by 8, and then you multiply 3 by 8, which is 24. So 1 minus 2 is -1, minus 24 is -25. So you have -25/8. And that is our y value. So this is y, this is x, and so our vertex is 1/4 and -25/8. Okay, so the next step. What is the vertex form of the equation? That is a great question. And the way we solve that, well, it actually specifically asks us to use the method of completing the square to change the function into vertex form. And the way you do that is first go ahead and write out the function. I'm going to go ahead and just kind of create a little division here to separate the two main parts of this problem. So go ahead and write the original function here. F of x is equal to 2x squared minus x minus 3. And what you want to do is go ahead and factor out the 2 from these two terms here. So go ahead and pull that out. So you have 2 times x squared minus 1/2 x, and then minus 3. Now this is my way of doing completing this square. There are multiple ways you can do this, but I will be showing my way. And I actually noticed that Professor Brown has a different way in her previous answer keys. So when in doubt, just use her method, because that's the one that she's going to accept. All right, so let's go ahead and continue with this. So now what you do is, knowing that with perfect square terms like this, I had to think for a second what the word was, where you have some number or whatever next to the x here that's being subtracted or added. Let's say, okay, we'll just put 2. And you square it, right? When you FOIL it out, so FOIL, and I'm not going to write the whole method of, well, actually I am. So if we have x minus 2 times x minus 2, so you multiply the x's together first, you get x squared, and then you multiply x times negative 2x, and then negative 2 times x, also minus 2x, and then negative 2 times negative 2 is plus 4. And so what ends up happening is you get x squared minus 4x plus 4. Now notice that this term that's next to the x in the term here is half of this term, right? And so that's why we're dividing this term by 2, because what ends up happening is it allows you to create a term that has x raised to the first power with an extra bit of information, and then you can square that. And so you're basically simplifying that this guy into something much easier to work with. So let me go ahead and show you what that will end up looking like for this problem specifically. So let me just erase all of this here. Okay, so we divided it by 2, and so we have it in this form where we have x squared minus 1/2 x, and we're missing a little bit extra, but we're going to pretend that it was in the form that I showed before with the x squared minus b over b, b x plus c, which turns into x minus b over 2 squared. And that can be plus or minus, it doesn't matter. So same thing here. We don't have that c value, but you're going to see that it will come into play once we've done the method of completing the square. So this we just automatically know becomes x minus 1/4 x, not x minus 1/4, because that is the beauty of completing the square. And so you go ahead and square the outside. Now, if you notice, this minus 1/4 here, or the 1/4 specifically, matches the x value that we got in the vertex coordinates for the previous section. That'll be important. Okay, so remember how I said that we're missing the c? Well, we're not actually missing the c. We just haven't accounted for it in this problem, right? So in the function's current state, if you go ahead and FOIL this out, what you're going to end up with is x squared minus 1/2 x plus 1/16, okay, minus 3. And so when you factor in the 2, you get 2x squared minus x plus 1/8 minus 3. Okay, so now we have a slight problem, right? Because what that equals is 2x squared minus x, which is the same, minus 2 7/8, which is not what our problem or the function was originally. It was minus 3. So that means we have to subtract an extra 1/8 from that, right? So when we get this term here that you move the squared out using the completing the square method, what you end up doing is introducing a new value into there, right, based on the FOIL method, right? And so you have to account for that. So if you're going to add in a value here, you also have to subtract it. So you can go ahead and write what you're removing from the outside of the equation. And so what this ends up being is 2 times x minus 1/4 squared, and then the common denominator with 3 over 1 and 1 over 8 is actually 8. You just have to multiply the 3 over 1 by 8 over 8. You get 24. So this part is negative 24 over 8 minus 1/8, which gives you negative 25 over 8. And so what you'll notice is that this 1/4 is the same as what we got here, and then the negative 25 over 8 is the same as what we got above. The only difference is that the sign inside of the parentheses is flipped. And so what that tells you is that your vertex, right, is h and k, where this is h, and this is actually negative. Which one is? So the standard form is a times x minus h plus k. Right, so this is minus h. That means that the 1/4 is going to be positive. And that's for the vertex form of an equation. So vertex form, and I'm missing a squared here. Okay. So the final answer for the vertex form of this equation is 2 times x minus 1/4, sorry. Kind of erased that little line there. Squared minus 25 over 8. So now if we go ahead and graph this function, we have to use a little intuition about transformations of graphs and our fundamental functions. Now this function that we're graphing here is the quadratic function, meaning it's going to look like a parabola, right? And let me go ahead and choose a decent color for this. So it's going to look something like this, but moved to another location on the graph. And you can automatically determine where it gets moved based on the vertex form of the equation, right? So vertex form is, again, 2 times x minus 1/4 all squared minus 25 over 8. And so go ahead and put down some tick marks. So this would be 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6, 7. Okay. So it starts at 1/4 and minus 25 over 8, which is just over 3. That's 3 and 1/8. Negative 3 and 1/8. And of course, that's just 1/4. So the x value is at 1/4, which is about here. And let me go ahead and not raise that up. So that's the x value. The y value is negative 3 and 1/8, so about here. So when you combine those two, your vertex point is right here. Right here. And we also have this 2 over here, which means that it's scaled up, right, vertically. And so that looks something like this. It's like a pulled parabola. And that is the solution to that part of the problem. Oh, one other thing. We also found the zeros of the of the equation, which we're at 3/2 and 1. I think I actually made a mistake with the one thing. Oh, right. That's not 4/4. That's -4/4. I apologize. So this would be -1. -1. All right. So now you have an x-intercept here and an x-intercept here. So when you draw the parabola, you have to make sure it passes through those points. And that's how you do that. Okay, so that is the first 4 problems. Let's move on to the next set here. And it says, given m of x is equal to 2x times x plus 3 times x minus 5 to the 4th power, what are the zeros and their multiplicity? Well, the zeros are the values of x for which this function is equal to 0. And based on what's called the zero product property, anything times 0 is equal to 0, right? So all you need to set this equal to 0 is for any one of these to be equal to 0, any of these terms here. So the 2x, the x plus 3, x minus 5. That means that you are literally going to set them equal to 0 and solve. So I'm actually going to go ahead and do that over, I can't erase that far. Okay. Go ahead and do that over here. So 2x is equal to 0. X plus 3 is also equal to 0. Or find where that's equal to 0. And find where that's equal to 0. And don't worry about the 4th power right now. And so when 2x is 0 when x is equal to 0, right? Because you just divide both sides by 2. You're just solving for x, basically. And this is 0 when x is equal to -3, because you're adding 3 to that. And this is 0 when x is equal to 5. Okay, now let's go ahead and worry about what the exponent means. Okay. So technically these all have exponents. This is just 1, this is 1, and this is 4. That means that the multiplicity is the number of times that those specific zeros show up, right? And that's based on the exponents that you raise their terms to, right? So the multiplicity of this first one is 1. Multiplicity 1. This is also multiplicity 1. And this is multiplicity of 4. 1, 1, and 4. Okay. And what is the graph behavior at each 0? That one depends on some rules of how these functions behave with certain multiplicities. So the general rule is that if the multiplicity is odd, then it crosses. If it's even, then it touches. And let me just make sure that I have that correct, because it's been a while since I last did that specifically. So let me just... Okay, so after doing some quick Googling, it turns out that I am correct. So when the multiplicity, when the exponent related to, or the number of times the root shows up is odd, so 1 time or 3 times or so on, then it crosses. And that means that when the function does something like this, where it'll touch the thing, touch the axis, the x-axis, and then go past it, whether that's going down or going up. Now, for even, what that looks like is it'll just touch and not go past it, right? And that intuitively makes sense, because if you're with even powers, you can never produce a negative value unless you plug in a complex number or an imaginary number, which is kind of outside of the scope of this section. Okay, so therefore, let's go ahead and list our value, our zeros here. So x is equal to 0, x is equal to -3, x is equal to 5. The multiplicity of each is 1, 1, and 4 respectively. And so the behavior is that the function will cross at 0, cross at -3, and touch at 4. And that is the solution to that problem. And so on to the next one. We have this funny one here. I kind of cut out the majority of the problem because I wanted to focus on just explaining the property of the problem and how to apply it to other problems. So in the original question, it basically gives you this function here. F of x is equal to -0.03x squared plus 1.8x minus 24. And it asks you to determine what is the maximum height that can be reached using this function. Okay, and so that takes a little intuition in understanding how this problem works. But the idea is that this is a quadratic function because it's a polynomial equation or function, and the highest power is 2, so it's quadratic. And so we know that it's going to look like a parabola. And parabolas come in two forms, right? There's the regular parabola where it goes down and then comes up. And then there's the other parabola, which is just the mirror of it over the y-axis that goes up and then comes down. And we know that for quadratic functions, it has a pretty neat property where the either minimum or the maximum value will be at the vertex, right? And it's a minimum if it's a regular function. It's a maximum if it's negated, right? So if the coefficient in front of the x squared term is negative, so a is less than 0 in ax squared plus bx plus c. And that's just math speak for saying, given some value of a that's multiplied by the x squared term, it's going to be less than 0. It's going to be negative, right? So if we take a look at the function that we have here, it's negative 0.03. And right off the bat, we have the negative. That means that we can find the maximum by looking for the vertex of this equation. And so how do we find the vertex? Well, we just do what we did for the first section that I went over. And to do that, we just know that x is equal to negative b over 2a, which in this case, negative b is negative 1.8, over 2a, which is 2 times negative 0.03, and that is equal to negative 1.8 over, and again, I'm just like being very thorough about my work here to show each step that I'm doing for this. Now, since we're working with decimals here, and I don't particularly like working with decimals at times, like they're wonderful for certain things, but for some other stuff, they're not so fun to work with. A neat trick that you can do if you kind of just want to get rid of the decimals from related terms when it's like dividing or whatever, is just multiply by some multiple of 10 to kind of just get rid of the zeros, basically. But you have to be smart about how you do this. Okay, so we know that we want to move this over by 2 decimal places. That'll give us just a regular integer number, so 6, which is a lot nicer to work with. And then if we multiply by 100 down here to move the decimal places over, we have to multiply by 100 on top in order to keep the fraction the same. So negative 1.8 times 100, you just move the decimal over 2 times and add the 0, so negative 180. So the negatives cancel, and 180 divided by 6 is just 30. So x is equal to 30. Now y is equal to f, the function, at the x value that you found at 30. So let's go ahead and do that. 30 squared times 30 minus 24. And that is equal to negative 0.03 times 90 plus 1.8 times 30 minus 24. And so that is equal to 90 times 3 is 270, and we have to move it over by 2 decimal places, and it's also negative. So that would give us 2.7, and that's negative. And just to, okay, so plus 1.8 times 30 is, so 1 times 30 is just 30. So that's 30 plus, and then 0.8 times 30, well, that's just 4/5. So you remove 1/5 of 30. 1/5 of 30 is 6. So you remove 6 from 30, that's 24. So you go ahead and add 24 to 30. That'll get you 1.8 times 30. That's kind of the fast way of doing it. That is how you just do multiplication. But if you find yourself having trouble doing it in your head without a calculator, just remember to split it by decimal place. And then subtract 24. So this 24 and this 24 cancel each other out. And we are left with, let me change my color. So negative 2.7 plus 30. Oh, I actually made a mistake. This isn't 90, this is 100, 900, sorry. Apologize. Guess I must be like really tired for some reason. So instead of it being negative 2.7, it would actually be negative 27 instead. Okay, and so negative 27 plus 30, or 30 minus 27, is equal to 3. So the answer is 3 inches for the original problem. Okay, so let's move on to the next one here. For the graph shown, which you may recognize as some form of a rational function, as x approaches, so it's asking us to write out the behavior of the function at these limits, right? So as x becomes a very, very small number, negative infinity, which is over here on this side, the function, this guy, approaches a certain value. And I didn't really add in the tick mark details, which are exceedingly important here. So let me go ahead and add that in. This is really the important value here, but I'll go ahead and add in some more. Okay, and so, oh, wow, that's deleted. I'm deleting everything but what I want to delete. Okay, so you'll have to pardon how messy this graph looks. Just pretend this is like straight up and down the line on the left. Let me try redrawing it, see if I can do a better job. Okay, one more time. There we go. That's a little bit better. Okay, so we have two different asymptotes here. Okay, a vertical one and a horizontal one. And so as x becomes very, very small on this side, the value that the function approaches is the horizontal asymptote, this pink line here, which crosses at 1. So f of x approaches 1. Now the next one is as x approaches 2, and pay attention to this plus here, that whenever you have a sign here, the negative or positive sign, what that means is that's the side that you're coming from. So if it's negative, you'll look from the negative side, and if it's positive, you'll look from the positive side, right? And that's if you draw a line on your point, everything after it will be positive side, everything before it will be the negative side. So in this case, we're looking from this side, and you can see that it approaches positive infinity. Now the range is all values that the function lines up with the y-axis with. So for each of these points, you can kind of draw from the graph to the y-axis, and it looks like every point corresponds with some value on the y-axis except for where we have this asymptote here, this horizontal asymptote. And so that means that the range, wow, I have just butchered my graph. So the range is everything excluding the value of that asymptote, which we determined was 1, right? So that would be from negative infinity, everything less than that asymptote, up to, but not including it, and then everything after it, up to but not including it, or down to but not including it. And so those are our answers for this problem. We have the end behavior, or the asymptotic behavior, and the range in interval notation. Okay, so let's move on to the next problems here. Okay, so the next problem that we have to do is number 13, which says graph the rational equation. Okay, so this one relies on your knowledge of transformations. So the first points that we can pay attention to are this 2 and the 3. Remember that this is similar to what we saw with the vertex form, right? Where you have the x with some value inside of its function operation, and then the y intercepts on the outside, just hanging out. So, excuse me. So this will be negative h, and this will be k. And remember that the vertex, or the point of origin, I guess you could say, would be h and k. So basically you flip the sign of whatever's next to the x value. So that would be at 2 and 3. Or really what I'm saying is, whatever happens to the, that's negative 2 and 3, not 2. Whatever you do with this function, you must make sure that you shift it over to the left by 2 and up by 3, right? And so normally with rational equations like this, you have a vertical and horizontal asymptote, and they all cross at a particular point. In this case, it's the, I guess for lack of a better word, vertex. So that crosses at that point here. Now, it's important to notice that, let me see, what color do I want? I'll use this one. That this is squared, right? So it's a rational function, but the denominator is squared. What that means is that it can never be negative, right? So normally with rational equations, you're going to have something that looks like this, where you have the two sides and they're opposing one another, right? So one goes up to infinity, or comes down from infinity and goes to the horizontal asymptote. The other goes from the horizontal asymptote down to infinity. Well, that's only because with the regular function, like 1 over x, it has an odd power, meaning that negatives are allowed, and so that flips the sign. But if negatives aren't allowed, then you don't flip the sign, and so it's all positive. So you get the same sort of behavior, except it's on the positive part of the y-axis. So that's what the rational function will look like to some degree. You have to forgive my terrible drawing here. And so the domain is just the standard form of the rational function domain. It's everything except for where the denominator is 0. And so the denominator is 0 at x is equal to -2, because -2 plus 2 is 0. And 1 over 0 squared is 1 over 0, which is undefined. so we can go ahead and say that the domain is everything from negative infinity to, we said, -2 exclusive, and then from -2 to infinity, and that's the domain. And the equation for the vertical asymptote, well, that vertical asymptote is this line right here, which is located where x is equal to -2. So the equation is literally x is equal to -2. And that is the solution to the problem. Up next, we have question 16, which says, given the graph below, is it one-to-one? Okay, so that relies on your understanding of the definition of one-to-oneness. And what that means is that for every y value, or for every value in the function, each of those corresponds to only one of the other, meaning that there will be one y value for each x value that you plug into the, that there's one specific y value for each x value that you plug in. Well, looking at the function, there are two x values that line up with each accepted y value in the function. That means it's not one-to-one. So it is not one-to-one because we can say each y value in the range, or each value in the range, corresponds to two x values. And as an example, let's say x is -2 and x is 2. Well, it turns out that that corresponds to 1 for the -2, so f of -2 and I think that is the best f I've ever drawn. F of -2 is equal to 1, and f of 2, or +2, is also equal to 1. Therefore, and this triangle dot pattern here means therefore it is not. One-to-one. Okay, pretty straightforward. Just look for duplicate values. If there are no duplicate values, then you know it's one-to-one. Easy peasy. Okay, so next question says, what is the inverse of f of x is equal to 3x minus 1? To solve that, what you basically do is you move all of the operations over to the other side, right? And so what I'm going to do is I'm going to replace f of x with y. I'm going to say y is equal to 3x plus minus 1, not plus 1. And so the inverse is basically solving for x, right? So we go ahead and do our basic rules of solving for variables. Go ahead and add 1 to both sides. So we get y plus 1 is equal to 3x. And then you divide everything by 3. And so what you get is, I'm going to go ahead and put x first. X is equal to y plus 1 over 3. And another way to put that is f inverse, the -1 there is inverse, is equal to x plus 1 over 3. Now notice that these two guys, even though the variables are different, are the same thing. They just kind of, I guess the word is semantically, mean different things. Like this form on the bottom is the more explicit way of saying this is the inverse that we're looking for. Okay, so the next question here is pretty similar. It's just saying using composition of functions, prove f of x and g of x are inverses. Okay, so that relies on a rule of inverses where it says given a function, so given f of x and the inverse of that function, then f of the inverse of the function or the inverse of the original function, so composition of those, will equal the input, will equal x. So what that means is if f of g of x, or not of, or g of f of x is equal to x, then they are inverses. And so let's go ahead and solve that. Go ahead and plug in the, it doesn't matter which one you choose. So I'm just going to do the f of g. So if f is equal to, let's do it this way. We're plugging in g of x. G of x is equal to x to the third plus 5. And so that is equal to the f function, the cube root of x, which we're replacing with x to the third plus 5. So x to the third plus 5 minus 5. So go ahead and expand the inner part out. We get x to the third plus 5 minus 5. And those two guys cancel each other out to 0. And so we have the cube root of x to the third. And so another way to rewrite that is x to the third divided by third, right? Because that's another way of writing root functions or radicals. And so that's just x to the 1, which is just x. So we got x, therefore f of x and g of x are inverses. Pretty straightforward. Okay. So we've got two more problems here, and I've kind of done a little bit of writing for the first one. This one says, solve the following inequality. X plus 4 times x minus 1 times x minus 3 is greater than 0, and use interval notation. Okay, so this function, using some intuition, it's greater than 0 when none of these terms are negative. Or I should put it this way, when an even number of these terms are negative. So that can be 0 or 2, right? Any other time, and it's less than 0 because you have a negative. So you'd have like a negative times a positive, and that results in a negative. But if you had like a negative times a positive, the two negatives would cancel, right? And so having an even number of positive terms would mean it's greater than 0. because it's not negative. Now, that also means that you can't have 0 be an answer because it's greater than 0. That means each of these cannot end up being 0. So this can't be 0, this can't be 0, this can't be 0. No. And these are 0 when x is -4, when x is 1, when x is 3. So if you just say that they are either greater than or less than, then you're good to go. So let's go ahead and figure out where we have an even number of negative values here for each of these terms. Well, this is negative when x is -4. So if we go ahead and create a little number line here, go ahead and put down -4. And it's also when x is less than -1, not -1, +1. And also when x is less than 3. Go ahead and add the 0 just for reference. And so above 3, each of these is positive. So with 3, because this would be 3 plus 4 is 7, 3 minus 2 is 2, and 3 minus 3 is 0. So when x is greater than 3, sorry, this will be positive, positive, positive. That's good. When x is greater than -1 but less than 3, then the x minus 3 will be negative, right? And why do I keep writing -1? Let me go ahead and kind of clean this up a little bit. When x is greater than 3, and x is less than 3 and greater than 1, then, so let's say it's like 2, right? So we plug 2 into the first one. 2 plus 4 is 6, which is positive. 2 minus 1 is 1, which is positive. 2 minus 3 is -1, which is negative. So that's no good. That won't fly. And then the next interval that we have to check is between 1 and -4. So x is greater than -4 is less than 1. So we can try something like, I guess 0 is pretty easy. 0 plus 4 is 4, which is positive. 0 minus 1 is -1, which is negative. And 0 minus 3 is negative. So we have 2 negative values here, which cancel each other out, makes a positive. So that'll work. And the last interval that we have to check is x is less than -4. And so if we plug in like -5, we have -5 plus 4, which is negative because that's -1. And then we have -5 minus 1, which is -6, also negative. And -5 minus 3 is -8, it's also negative. So 2 negatives cancel, gives you a positive. We have 1 more negative here, which makes it all negative, which means that will not fly. So the only intervals that we have that work for this inequality are when x is greater than -4 and less than 1, and when x is greater than 3. So using interval notation, remember that these are exclusive. So we'll go ahead and say from -4 to 1 excluding both, and from 3 to infinity, also excluding both. And that is the solution to that problem in interval notation. Now the last problem that we have here is solve the following inequality. 5 over 2x minus 7 is greater than 1. Okay, so in order to solve this, we can use a little bit of interesting algebra here. We can basically solve it like a regular algebraic equation solving problem, right? Now, you have to be very careful when solving these inequalities algebraically, because there are certain rules that you have to be aware of when doing it that will flip signs. So I believe if you have like an x squared and you square root both sides, you have to be careful because you have to add like a plus or minus or something along those lines. Square roots also cause issues, and negatives. Now, I don't remember all of the rules specifically. You'd have to look them up or ask Professor Brown, but do be aware that there are some pitfalls that you might face when solving inequalities. But for linear, somewhat linear inequalities like this, where the greatest power is 1 and there are no funky things happening, you can just solve it like a regular algebra problem. Let's go ahead and we're just going to go ahead and treat this like an equal sign and multiply both sides by negative, not negative, multiply both sides by 2x minus 7. And so that ends up with that canceling. We have 5 is greater than, and we'll keep the equal just to remind ourselves that we're pretending it's an equal sign. And then add 7 to both sides. Go ahead and use red. And so we end up with 12. On one side and 2x on the other. Divide both sides by 2. And our final answer is, now, check this out. You have to be careful, because I'm moving the x to the other side. That means I have to also change the orientation of the symbol in the middle. So instead of it being is greater than from left to right, we'll say it's less than from left to right. So x is less than 12 divided by 2, which is just 6. And so that is our solution. And we'll go ahead and write this in interval notation. So from 6 exclusive, oh, hang on, x is less than 6. So it's actually from negative infinity to positive 6 exclusive. And that is our solution. And that is the last problem in Professor Brown's 2015 Test Review 3. And so that is the end of our review. Good luck on your exam, and wish you the best.